Now, third and final speaker is speaking from Bristol, Mark Handover, who's an applications engineer at Mentor Graphics. Mark is going to speak on how secure is your system. Mark has been involved in design and verification of complex SoCs for 20 years. He currently works as an application engineer with Mentor Graphics, focusing primarily on the areas of load power, formal, and assertion-based verification. Okay.
Thanks, Mike. Hear me okay? Yep, good. So good afternoon, everyone. As Mike said, my name is Mark Handover. I work for Mentor Graphics. I want to talk you through what Mentor Graphics are doing in this area. In some respects, I want to take you through a little bit about what our customers are telling us, how we've implemented our solution. I'll talk you through some of the specifics of the solution, show you some of the likely results you're going to get if you're going to run this. And then at the end, we'll have a case study just to show you what one of our customers is doing with this in the real world. Bear with me. Problem with the slide. There you go. Yep, that works. Thank you. So I think this has been mentioned a number of times before, but there's plenty of documentary evidence out there, plenty of things in the news about things going wrong. I was going to play a video of some of this, but we can't run videos in DVClub, so I found out. So anyway, I've got the links to these if you're interested. I'm sure you've already seen these anyway, but these are good examples of security issues that are coming as challenges. So the two you can see here are to do with the automotive industry. And this is relatively new for this industry, so this is a kind of new problem that they're discovering and trying to get a handle on, where they can grab control either directly or remotely of internal buses such as the CAN bus, and then they get access to your car. I think there's an example as well where they got in through the DAB radio and were able to gain control of the car, which is obviously very concerning to the manufacturers and to us as consumers. And so they're now looking at other techniques, and there's a whole, obviously, drive to secure these systems very quickly before we get to things like self-driving vehicles. And there's other areas as well in the market that are equally interested or should be interested in security. So Dave mentioned the one about the heart issue. There's another one here about an insulin pump that was they were able to take control of, and indeed just general medical equipment in hospitals. So all of this runs wirelessly, and it's easy to get control of this. And so obviously there's a great concern about being able to secure these systems better. So what can be done to prevent these kind of issues? So we've heard a number of times, it's all about key storage. So signing packets and systems with secure keys, and then make sure that the key storage in the hardware is absolutely secure. So here's another example, another different way of looking at it. So we have some system here. So this is an SoC comms controller. So you can see we have our key storage highlighted there in green. So this is the bit we want to protect. And the path, the only path that we want to access that is through the encryption engine. So you can see as a system we have different interconnects, different bridges, controllers, interfaces to the outside world. We want to make sure this is secure. We don't want to have that key storage leak out of anywhere else except the designated path through the encryption engine. So we don't want to be able to access the key storage through the microcontroller or out through the AXI, for example. So as hardware designers, verification engineers, we need to make sure that this is true, that the key storage is only accessible by the route that we decide, and that every other path, by definition, is insecure and should be secured. So the bad news, current methodologies, manual inspection and simulation aren't going to scale for this. Okay, so you know, we have experts in companies which are experts in security, experts in their own systems, And probably until fairly recently, they were able to inspect these things and say, okay, visual inspection is enough. I can, work out how the systems are operating, and we can guarantee as much as we can that these are secure, and that all the open paths have been closed off. And then even if you turn to simulation, constrained random is great, but it's not exhaustive by nature. And with the awareness of these security issues going up, then obviously the fact that we're not using exhaustive techniques is going to become concerning. So how can formal help? So Dave talked about some of this before, so let's just cover this again. So standard formal approaches aren't going to work, actually. We need to move to some secure app or focused solution for this. So handwritten assertions, we could do it, but you're going to need thousands and thousands of these, okay? And you need to then know all the paths, pretty much, that you want to check in order to write an assertion to go and check this. So it's not really a good solution there. Connectivity checking you could use, but connectivity checking is really about checking point to point of a described path. So you're going to say, okay, this point is connected to this point. Checking for absence of connections is not really tractable with normal formal verification with regular model checking because of the volume of the assertions and the knowledge you need to have about the design itself. So you need a specialized app where you can describe these paths that you're interested in, and the tool can do the grunt work for you. So our customers came to us, a number of them, and said, okay, we need something different in this space. We need a solution that we can get tractable results, results in a good time frame, and robust results. And so R&D went away. They came up with a solution which we call Quest to Secure Check. So Secure Check sits in the middle here. It takes your RTL. It takes some specification of what you want to check. So you can describe at a very high level the paths or the operations you want to check from your key storage to the outside world, for example. So you specify this, you load that with the RTL, and Quest to Secure Check generates underneath the hood. It will generate the checks it needs to run based on what you supply in the specification, and then does the analysis of those. We can find things like ports in your design and the black box inputs. If you're black boxing parts of your logic, or you want to check to specific IP that's embedded in the design, we can do all that automatically for you. And this has been mentioned already, confidentiality and integrity check-ins, and I'll cover these again as well, just to explain those further. So we can do the different types of checking. And this automatically happens under the hood, okay? So you just need the RTL, you just need this high-level spec, and then the tool will go away and do most of the work for you. And then obviously there's a debug aspect to this as well. You get an insecure path flag. You want to go and debug that, and I'll show you what the results might look like. So this is the kind of coin here, if you like. So you're going to run. You're going to probably see insecure and secure paths. Okay, an insecure path by definition is the path you're probably expecting anyway. So the path from the key storage to the encryption engine is an insecure path. It's just one that you were okay with. There may be other ones that you will need to fix. So you may see lots of insecure paths you need to go away and fix. And then hopefully you'll see secure paths as well, which are those paths that you can sign off as good. Okay. And then as part of that, the secure check analysis does the two levels, so in confidentiality and integrity. So checking from some internal secure keys, some internal memory, whatever it might be, to some outside world. So can the data make its way off chip? And then equally the other way, integrity. So you have your storage, your key element that you're trying to protect. Is there some way to affect it? So to look at it kind of graphically, confidentiality is about one source, many destinations. And this is where some of the challenge lies. So you're saying, okay, I have my key storage, I just make sure it doesn't go anywhere else other than some route. So it has many endpoints, if you like. So if you look at the diagram, we have the key memory on the left-hand side there, and the system to the right. And then you can see here we have various colors indicating whether things are expected, illegal, as in an insecure path in red, or a secure path in green. And then looking at it the other way, so the integrity verification, you have your key memory again, and now you're checking paths kind of on the input side, going to somewhere you expect. So cached key in this place. And so this is just making sure that the key can't be affected, so you can't overwrite it or change it or do anything else to it. So when you run secure check, you load the RTL. I said you need to kind of some way to describe the expected paths. So this is what it might look like. So if we look at integrity at the top first, we have a small bit of script here. The smarts are in the red. So this is describing the path. So we have a command assertion create path, and then you just specify the from signal and the to side of things. So we have a little bit of TCL there to go away and find the ports. So we've extended some TCL here, so we can say, okay, find the ports. They're all inputs, and they're from a particular module, and then we load that list up into the assertion create path directive. And so we're saying, okay, from, in this case, all inputs to the udecoder my key section, okay? So this is an integrity, so it's going from the outside world to the key. On the confidentiality side at the bottom, excuse me, we have a couple of examples here. So the top one, we've explicitly listed a path here. So rather than using TCL to go away and populate a list, we've called out a specific path. So from our data in a FIFO, which would be our secure memory in this case, perhaps to some external pin PR data. You can see on the right-hand side here we have a dash from condition as well. So now you can, you don't have to, but you could specify conditions as well. So it may be that there's some conditional element that you need to apply in order for this path to be valid or wanted to be checked. Okay, so it could be some valid signal or some enabling condition that you want to qualify the path with. And so you can do that on a from and a to basis as well. And then the bottom example here, you'll see we have a create path from our data to some dollar expected port list. Okay, so this is useful. So when you run the tool, you'll see a bunch of insecure paths, but some of those you would be expecting, and so it'd be nice to highlight those separately. So you can say, okay, out of this list, there might be one or two paths that I'm expecting, and so you can see the kind of wood for the trees. What we can do is create a list of expected ports and then give it the dash cover option. And the tool will then go and prove that not only are those insecure paths available, it can flag them separately and say, okay, these are the ones you expected to see as well, so we can tag them differently, essentially. But it will prove that those are really insecure paths of the type that you expected. So it allows you to just do an extra level of verification. In terms of results, so this is the kind of thing you might expect to see. So we have color coding in here. So obviously you're looking for secure paths, so the green paths. This is the good paths, if you like, so the way the data can escape off chip. So this may be, you might be looking at all the outputs of your device, and 99% of those outputs might be classed as secure paths, and so that's all good. Covered, the blue ones. So these are the insecure paths that you expect. Okay, so those exceptions that you listed. That you expect to see, so those maybe remaining couple of outputs that you expect to see. Insecure paths, the red ones, so these are ones that you need to go away and debug. Okay, so these are either insecure, data found away off chip, or if it was an integrity check, you were found some way from the inputs to the key, or a path that you said should be insecure and coverable that we couldn't cover. Okay, so some path you expected that we weren't able to cover. And then, of course, you may get inconclusives. This is formal after all. So, capacity limitations, state space limitations still apply. And so if you get some inconclusives, you're going to have to use kind of regular formal techniques for trying to reduce the complexity, such as introducing black boxing or cut points or certain abstractions, maybe some constraints and so on. In terms of debug, so you get your results, you run the tool, it runs for some time, it drops out, gives you the paths, you bring up the database inside the debugger. This is kind of what you would expect to see. So we can see at the top, towards the left, some red and green icons, so secure paths, insecure paths. The red ones are going to be the ones you want to debug, obviously. And then you have various ways to debug this. Obviously the traditional waveforms. And I'll show you some more detail of what this looks like. You can go to the source code and trace through the source code and follow the data through the source code. You can view schematics, so you may want to visualize the path that the tool is talking about, starting at the from point and going out to the outputs or the to point. And so you can do all those things. In terms of waveforms, there's a number of different waveforms you can bring up inside SecureCheck. But what we're doing is basically tagging the data. So this relates to the question you had, Anthony, I guess, about what we do here. So we place a tag, a data stream, a data element in the from point, if you're doing a from kind of to, and then you can actually follow that through the system. So this is a path through the design. So you can see the red strobing here. This indicates the secure data, the secure tag, or the data tag that's passing through the system, and you can follow it all the way through the hierarchy, all the way to the outputs here as it's dropping out of the chip. The data, the tag, can obviously be different because the secure path might be dependent on the data that's in, that you're actually implementing into that data word anyway. And so what we can do is show you multiple versions of this and show you where they separate. So like a waveform diff, if you like. So we can implement two different tags, and you can follow the two different to see where they diverge. But you're effectively following the data through the system here. And then in terms of schematics, so again, this is maybe what you could expect to see. Obviously, it could be more complex in some cases, depends on how long the path is. But you'll end up with a schematic like at the top half here, which is the kind of full path. So on the far left is your from point, if you're doing a confidentiality check, so your key storage, out to the outside ward or whatever you define as your 2 point here. The blue kind of tags you can see blowing up in the bottom two pictures. So we actually label the from and 2 point. Obviously, schematics can get, in some cases, cumbersome and complex. Sometimes you bring the schematic, it may be difficult to see where the from and 2 points were. And so we actually label them here. And you can obviously push around and add detail in the schematic as you go and cross-probe to the waveform, add annotation, all that kind of good stuff that you'd want to do. So just a quick single slide on a customer case study. So one of our first engagements was for actually a worldwide consumer electronics company. So based in the US. They manufacture high-end entertainment systems. So this is probably one of the worst scenarios for security. Not because of risk of life, but because of the amount of attacks they get. So they get 24/7, 365 attacks. Why I say it's worst case, this is a consumer product, so the hackers can go into any store, buy hundreds of these things, and have them, attack 24 hours a day in parallel. And so these guys are under huge amounts of pressure to make sure this stuff's secure, so that they make their money. They didn't have any real formal expertise in-house before this, so they were using manual inspection up until this point and simulation technologies, and they were finding that these just weren't scaling anymore. They needed to move to something else. They looked at software solutions, but found they were incomplete. They actually went somewhere else before they came to us, and didn't like what they saw. So they weren't getting the performance or the results out that they wanted. So they came to Mentor, and sure, we engaged with SecureCheck. And, well, okay, they were impressed with the speed of analysis. The results exceeded expectations. But probably crucially, all the expected paths were okay. They reproduced all the expected insecure paths that they already knew about. We actually found some new ones for them as well, which they were able to fix. And so, the result was a win for them, and obviously a win for us as well. So just in summary, stating the obvious, I guess, security is a growing concern. It's going to get worse. IoT is going to bring more problems or more concern, I think. Simulation, as we said, so simulation is just, it's good, it can be used, but it's incomplete, certainly for this kind of thing. Normal formal methods can be applied, but they're going to have challenges. They're going to be incomplete. You really need a specialized approach for this. So SecureCheck is being designed, with this particular problem in mind, as is the formal apps these days. A very focused technology on a very focused problem. And with that, I will leave you. Thank you.
Any questions? Just go to the previous slide. When you say normal form methods will have challenges, does that mean the engine's underneath?
No,
or
I mean
the way you write the properties?
regular model checking, regular handcrafted SVA. That's going to be challenging just because of the nature of the task you're trying to do here. Okay, so it's the one-to-many type of argument, the trying to verify the exceptions, not the known stuff. So it's just
following on from the previous talk, Dave, he was talking more about data flows. You were trying to verify that certain data can't flow from one place to the other. Is that the type of thing you mean? You've done it with your tickle on your ports.
Yeah, exactly.
Within your construct.
Yeah, so if I go back, where we go back? Yeah, so this kind of thing. So yeah, so the smarts, as I said, is in the red kind of commands here. So you have a command, you can specify at a very high level what you want to check. So you can say, okay, this is my key, and I'm going to flow elsewhere to the outputs or to some internal node in your design. The tool works out all the paths it needs to check. So you don't need to know them all in advance. You don't need to come up with some very clever SVA. You just need to specify at a very high level what it is you want to check.
Okay, thank you. Any more? Oh, sorry.
Just wondering if you have any experience of running this flow at gate level.
Not at gate level, no.
Okay, thanks.
It's a quick answer.
Yeah.
Obviously an FAE, not salesman.
Yeah, absolutely. We speak the truth, right?
Okay, I think that's it. Thank you very much. Thanks a lot.